So what is kinetic Monte Carlo? Anybody have any idea?
So from Isaac's talk, when he kind of introduced to us more fashion, it's rather than doing a kind of a rate, we do it at a rate where we kind of check as if it hasn't been done in a particular amount of time, there's a higher probability that it happens. No? Okay, so sorry.
You're close, but not quite.
Okay.
I mean, your statement is like, indicates some kind of maturity of chance, right?
Right.
It hasn't happened, and it's going to happen. That's not how this works. It's not how chance works.
Okay, so okay, fair enough.
If you take that limit to infinity, that's probably true. But on the next roll of the dice, it's not so sure. Right? That.
So you take all the.
Everybody get that? Yeah, if you're at the roulette table and it's been black 5 times in a row, it doesn't mean it's got to be red next.
There's a higher probability of it.
No, not a higher probability.
Oh, sorry, I shouldn't have said that.
It's totally memoryless.
Memoryless.
There's not a higher probability. Each spin is independent of the other. If you have an honest casino.
Which is like that statement, the memoryless property with a constant rate of something happening is enough to derive with what's not like that's it. That's fundamental to these. Basically, it means that
cool, but let's not worry about the Poisson distribution right now. So we will come back to that in a minute.
Yeah. So for this thing, we write down every possible thing that can happen, and we figure out the rate at which they can all happen, and we treat them as if they're all independent competing rates of reaction.
Yeah. Okay. So this is still Monte Carlo because we're still just going to draw a random number, and then that's going to decide what happens. Okay. But now we look at our whole system. Okay. And there's a bunch of different stuff that can happen. And each one of those different things that can happen has a rate associated with it. Cool. So your system can be in some configuration. And let's say it's possible to go to 3 other configurations. Cool. So when you draw a random number, it's going to go to one of these 3. Cool. Yeah. This could be a minor change, a particle jumping to the left or right. It could be a major change. It could be a whole redistribution or something, or some totally different event. A particle gets added. They're going to be added at some point. Okay. It doesn't really matter what these things are. What's important is that you have a rate associated with each one of them. Let's denote those are 1, 2, 3.
Are the rates similar in the same way that I would think there's a probability? Like, all your rates have to add up to like a 1 kind of thing? Like, are you still following on that?
Kind of. That is exactly the connection that we need to make.
Okay.
Okay. But for now, they're just rates.
Okay.
And rate is just over time. So what's the average time it takes if you're in this configuration to go over here? Take 1 over that, and that's the rate at which you do it, right? Cool. Is everybody okay with that? All right. So the rest of this falls out easily, as Austin's already used his intuition for. So the important thing is that you're able to have a system where you can define rates for how the system evolves. Cool? Okay. So to answer Austin's question, let's calculate the total rate.
So all of the systems are independent reactions, right?
Yes. Yeah. But what we'll see is that we can, when you get here, you can recalculate all your rates. Right?
Yeah, let's say like reaction 2 and reaction 1 like to happen together.
No, absolutely. That's not
it. Can't happen in kinetic 1.
There might be a way of doing it, but certainly not what we're going to talk about. Okay.
So the rate.
We can probably end.
Or like, I mean,
but if you have a rate limiting step, then you can subsume that into this rate.
Yeah. Like
so kinetic Monte Carlo doesn't care about the details of how you get from here to here. It only cares how long does it take.
Oh, okay. Certainly.
Yeah.
But if like if reaction 1 makes it like 99% probable that reaction 2 is going to happen, there's no way of calculating.
Oh, you're saying. But no, they're totally independent. I don't know if there's a way to modify it, but I think kinetic Monte Carlo, they're totally independent. Cool. Okay. So we have have this random number here, right? Which is, sorry, we have the total rate here, which is just the sum of all the rates. Can anyone think of a decent way we can use a random number to appropriately evolve the system in time in a way that is both random, yet it reflects the relative likelihood of these events at any particular time? I'm going to draw a random number, okay? And it's going to be between 0 and 1, right? Like we always have.
So then I would scale the rates appropriately to, say, some 1, and then just kind of pick out which rate I get based on whether I'm at 0 or 1. Right?
Whether you're at 0 or 1.
So like you pick your random number, say it's like 0.5,
yeah.
And then you'd have like you get to say R1 when scale goes from 0 to 0.4, R2 yeah. goes from 0.41 to like 0.7. So you're like, okay, cool, R2 happens.
Yes, very good. That's exactly what we do. Okay. So another way of saying that is to say we take our random number and we scale it between 0 and R. Okay. So random number we want to be between 0 and R total rate. Cool. And then this block can correspond to R1. And this block can correspond to R2. And then this obviously is R3. And then we just go, well, where did we land? Well, using Austin's example, we landed here. Cool. So evolve the system such that we go R2 happens. Cool. The event R2 happens. All right. Again, this could be a particle moving. It could be addition of a particle to the system. Maybe a particle leaves the system entirely. Maybe 2 particles join together to become a molecule. Okay, whatever. Cool. Everybody okay with this? So that's really all there is to it. There's one tricky question. We want this to reproduce the dynamics, right? So when this event happens, by how much should I increment time?
One over R2?
1 over
R2? No, maybe R.
Because that's just how long it takes R2 to happen, right?
R over it. Could be 1 over R,
Which are
big R.
yeah. Okay, so naively, you can take delta t to be 1 over R.
I thought Isaac said that the time test.
Yeah, no, we'll get to that.
Okay.
Okay, Isaac's brother didn't watch the video. Let's forget about Isaac. Okay, and let's try and build this from the ground up. Okay, do you see why it's 1 over R?
Average time with which a reaction of any kind.
Exactly. Okay, it's not just the average time for this guy to happen. No, we consider all of these possibilities could happen. One of them was going to. How long does that take? It's just the total of 1 over R, right? Cool. People okay with that? Kind of? Yes, no, maybe?
So R1 has a different probability of R2.
Different rate, which we then translate into a probability here.
Okay. It's a different rate, meaning the duration of R1 is shorter, or more R1s are happening?
When R1, it means the, we don't worry about that. We only worry about if R1 happens, this is the frequency of R1 happening. How often it happens.
Okay.
Yeah. Okay. So if an R1 event occurred, the average time for that to happen would be 1 over R1.
Right,
Yeah.
so we can have like 10 R1s occur per second, so we can't just increment it by a time step of 1, because when we have to actually go through it, we have to say, okay, we're going to have to hit R1 approximately-ish 10 times we go per second. Okay, think I know how it's going.
You could, if you wanted to do like, okay, at some point in time, I'm going to draw a random number and see if R1 happened. Draw a random number, see if this happened. Draw a random number, see if this happened. Well, this happened and this happened, and then I add up one of the times, right? And then that, but that's not what we're doing. We're taking one random number and we're deciding which one of these happened. Okay, and so we have to look at the total rate and go 1 over that.
Right.
Cool. So think of it this way: you have a system with a whole bunch of particles, right? And they can jump left or right. They have some time associated with that. Okay, it takes them so long to jump left or right. If you increase the number of particles, then for any one of them to jump left or right, for your in the evolution of your whole system, that's a small bit of time. Right? If you just have one particle, and it takes a second to jump left or right, and a second to jump left or right, second to jump left or right, second to jump left. Now you have 2. No, on average, both of them are doing it. So it actually only takes half a second for you to see one of these guys jump. Right? Cool. You get 3, it takes a third of a second. You get 4, it takes a quarter of a second. Cool. Because you're not looking at the probability of this guy doing it. You're looking at the probability of any of them. Cool. And that's what we're doing here. Is this okay with you?
Yeah.
Any problems? Yeah. That's good. There aren't that many of us, so everyone can say yes. It's not gonna. Not gonna blow us out. Okay. So naively, this is what we have to do for the time step, right? But this means that we have a constant time step. And so we won't have a distribution of times for events to happen. Okay? As Martin alluded to earlier, if you have a random process, look at the distribution of the time it takes, what do you get?
Well, the ones with the higher rate of reaction happen more often.
No, we don't even have to do it that way.
Oh, +1.
Yeah, it's just a Poisson distribution. Okay? We obviously don't get a distribution here because we have a single value. Okay? So what we can do is we can take delta t. That's not. We can take delta t to be equal to, this is my algorithm. Oh. I'm going to actually put them here again, so the next person has the same. Okay, delta t is equal to -1 over your random number, and that's over r. Okay, and this way, the mean of this thing is 1. So your average delta t is going to be 1 over r, but you're going to get the appropriate distribution.
What's the prime?
It's not.
Oh.
Cool? Is that all right with people?
So where does the 1 over 1
It comes from because this is necessary to get the Poisson distribution. And I'm not going to do that. Cool? Any questions?
It's not going to give negative time.
1 over your random number. This is a positive number.
That can be close to 0, so that's one of an enormous positive number, which is positive.
The rand is going to be close to. Rand now scales between 0 and r, right?
Right, so it's close to 0.
Right.
0 and positive. And it's 1 over 0 with like 10 million. But 1 over 10 million is a positive number.
This might be positive. Let's check in the code.
Okay.
I found competing definitions for this value. So it may be wrong in my notes. code works.
Do we just want to force number to be positive at all times?
No, that's not. The distribution should be like.
So we'll look at code in a minute, okay?
We had an R inside the block, then maybe that.
Let's look at that in a minute. Okay, we'll come back to that. All right. So an example of this, you may have heard of it. So people do this for surface science, right? You can have particles on the surface. They can be diffusing around, and chemical reactions can also happen at certain rates. Okay, so this is one that gets broadly used in that context. There's another nice example. From a young researcher at UOIT. Okay, and this is Hashcat. Right, and so this is a totally different context. But what Isaac and his students did was they found a way, basically writing Twitter as a series of rates. Okay, which basically translated to, as we just discussed, probability of certain things happening. Okay, so you can have a probability of adding a user, a probability that one of your users, of which you can have arbitrary number, follows, a user tweets, a user retweets. Okay? You set up probabilities of these different things happening. And then you just start selecting random numbers, and you can evolve your system. Cool? You can start building your network by adding these users, and you can start passing around information by having these tweets. Cool? So it's interesting in practice how you actually do this. Okay? Because remember what we want to do, we want to select a random number, and we want it to be between 0 and R, but we want to see where it falls in this. And we can have an arbitrary number of events, right? So how are we going to select which event occurs? How can we know what block it lies in? We can have a whole bunch of them.
We'll check forward.
Yeah, sure. But so here, so this is like between this is 0, this is 3, this is 7, this is 11, this is 45, this is 43, 50. Our total rate is 54. And so you get a random number, and it evaluates to 27. Right? All you know are these different rates. How are you going to match it up with the actual event? What happens?
No, so we can't just be like, oh, it's between 25 and 43.
Well, you can if you write this out every time in front of you on a piece of paper. Right? Oh.
Right. You can't even do
Right,
that.
so you're saying.
But all you know is that this is 3, this is 4, this is also 4, this is 14, etc. You only know the width of these blocks. Right?
I mean, you could write a big list of if statements.
Yeah, but we don't want to do that. And in fact, that's really complicated because we can add a user and then our total number of events changes. And our rates can change if we add a user. Right?
Right. So in this case, we can basically just sum up starting from R1, R2, R3, and then once we go over our random number, we'll just choose that last rate. That's the same thing because you're just running through the list.
No, that's good. That's good.
Oh, okay.
Yeah. But just reverse it. Okay? Take a random number, right? And say, okay, is it less than R1? Right?
In this case, no. So then we'll check R1 plus R2.
No, we'll take.
Oh, we'll subtract R1 and check R2.
Exactly. Okay. Minus doesn't equal. And then come here and check R2. Cool.
So basically be a statement. Same idea, we're traversing. We are just going to check every case. So
Yeah, but when you said then like a huge amount of ifs, I thought you meant if rand is between 0 and 3, 3 and 4.
Instead of hard coding it.
But what we want to do is systematically walk through.
Right.
Okay? Yeah. There are better ways of doing it. Okay? There are more efficient searching. You guys do searches in computer science. Right? You can use some of those techniques here. Okay? But this is a nice, simple way of achieving. Cool? Okay, so that's just one interesting implementation detail. And you see that on this slide as well. So if R1 minus the probability of that is less than 0, it's the same thing as doing this statement, except you take it to the other side. Then you do the event. Otherwise, you subtract off that rate. Cool, and then you check the next one. Cool. Okay, and so here's one of the definitions. For the time step, I think this is correct. Minus log, I think that's ln no. Minus ln R2 over rate total. So that solves our, I think that solves our problem. Yeah. Maybe. That would be possible. Yes, so R2 is a different random number that goes between 0. Yeah. Cool? Sorry with people? So we can evolve the system in time this way. We have an explicit time step, so we know exactly how much time has elapsed between different events happening. Cool? All right, and so this is a cool application of it, hashcat. But in order to actually look at the programming, let's step back and look at even simpler examples. So what I actually want to do, I mean,
Oh, I think I figured out what
we just talked about that.
like the formula we weren't sure about.
Yeah, we just.
Oh, did we?
Yeah. Yep.
Kind of off topic, kind of near you, but theoretically, you could do this rate process for like modeling a baseball bat or getting an information, right? Or the rate of first base, first, second base, third base, home, and then next.
So any system that you can describe as evolving, having events that take place with certain frequencies, so that you can define rates. Yes. Okay, so I want to take a simple system. I'm not sure if I actually have. Awesome. Hey. Showing off your code. Yeah, top secret. Okay. So what I want to do is take a really simple system where we have 5 states. Okay? And we're going to start by defining an energy for each one of those states. Okay? I'm going to start at an energy of 0. So at state 0, E equals 0. Okay? Then at state 1, we have an energy of 0.5. State 2, we have an energy of -1. State 3, we have an energy of -1.5. In state 4, we again have an energy of 0. Okay? And so this is what our system looks like. Our very simple system, just with 5 states. All right? We're going to take n particles to be in our system. we're going to have reflecting walls here and here. And I want to simulate this 3 different ways, all Monte Carlo ways. Okay? And I want to look at the long time state of the system. First of all, what is the long time state of the system going to look like? No, or keep it to yourself. Anybody? Anybody? So we really have a potential energy landscape that looks something like this. And these are infinite walls. And you dump n particles in there. This is like a n particles that have thermal motion. Yes, okay. Yes, exactly. Okay. The probability of being found in any one of these sites is going to be related to the Boltzmann. Cool. Which is E. So if we take ln of that, we can get the distribution. Cool. So we're going to find a lot of them here, a fair amount of them here, not many of them here, and some amount of them. Cool. Yeah. So we want to look at that 3 different ways. We want to come to that eventual conclusion. The first way I want to look at that is Metropolis Monte Carlo. So if I do Metropolis Monte Carlo, what do I do? What's my simulation approach for Metropolis Monte Carlo?
Well, you pick some initial position, then you flip it around based on the Boltzmann or the Metropolis criteria. Right.
We dump a bunch of particles in here. We can start them all at the same position. We can start them randomly placed through here. It doesn't really matter. Okay? And we start moving particles around. And then we calculate the change in the energy of the system when we move a particle from here to here, let's say. Okay? Or here to here. Well, if I move a particle from here to here, does the energy of the system go up or down? Down. Down is good. So we accept that move. If I try to move a particle from here to here, does the energy of the system go up or down? So do I reject it?
Only with some.
Right. We calculate the probability of this actually happening from the Boltzmann criteria by comparing these 2 energy states. Right? Take the exponential difference. That gives us some number. Draw a random number. If our random number is less than that, we actually accept this. Cool. So that's a Metropolis Monte Carlo simulation that we did. All right.
And we said Metropolis doesn't capture the time dynamic, right?
We're going to make it capture the time dynamics. Okay. But no, it doesn't. And what we just described, there's no reason that does, right? There's no time step in there. And we have all these particles, and we're just moving one of them and seeing the probability of that happening. Like, why do we think that would work? Right, we'll actually come back and make that connection. Cool. So that's one way to go about things. And that's in this code right here. So all I'm doing, I'm taking my particles. What am I doing? Where do I?
Start here.
Oh yeah, so the first thing I'm going to do is construct my probabilities of jumping forward and backwards. Okay? So I don't do the criteria each time. I can just calculate my probabilities like so. Cool. From any site, I can only jump left or right. So I can just calculate.
PP is PN.
P is probability of going forward. N as in positive. And it's negative. Cool. So I have those probabilities. This isn't really in Metropolis. I may have. No. Here we go. Oh yeah. So we need this for the agent base. We don't need this here. So here, all I'm doing is calculating my energy difference for a proposed jump, calculating my probability difference, or my probability based on the energy difference, selecting a random number, and then if that is a true criteria, then we execute the jump and make these changes. Cool? So notice I'm selecting a particle at random here, I, and then I select a different random number to decide if I'm going to try and go forward or backwards. Cool? If I go forward, I compare my energy. No, sorry. If it's less, this is backwards, because I'm comparing my energy to the site where I am minus 1. Cool? Is this making sense to people? A kind of Bosch explanation.
Did we get random?
Let's start from the beginning. Metropolis Monte Carlo. We pick a particle at random. Okay, so our index I is going to be a random number between 0 and an integer between 0 and n. Cool? So I've just picked a random number somewhere out of my random particle somewhere out of my n. 387. Cool? I select another random number to decide if I want to jump left or right. So this is going to be my proposed. Cool? If it's less than 0.5, I'm going to try and go to the left, right? If I'm already at the left-hand position, I can't go to the left, so nothing happens. This is my reflection. If that isn't true, then I can calculate the energy difference between where I am and where I'm jumping to. Cool? And I can convert this to a probability by the Boltzmann weighting. Notice that if the energy difference is negative, this is always greater than 1. So then this statement here, if rand is less than 12, is always true. Always jump to the left. Cool? Okay. So we look at this. If it's greater than 1, we always jump there because we're going to lower energy. If it's bigger, we do so with this probability. Okay, if I pass that probability check, I take away my particle from where I am, right? So my density of particles at the site xi gets less. My actual x position of my particle shifts 1 to the left, so it's also a minus minus. And now I can update my density of particles at my new position. Cool? Yeah? Okay. That was this random number here. That's if we try and jump to the left. We can do the exact same thing if we try and jump to the right. We end up with this energy difference. Now we're looking to the right, so it's +1 instead of -1. We calculate the probabilities, and we can again look at jumping. But now these minuses will be pluses. This is still a minus because we still subtract off 1 from the density of wherever we are. Cool? All right with that? Everybody okay with that? And then we can just dump our density profiles to a file at each time step. So we can see how the system evolves. Cool? Okay. Come back to this. I'm actually only dumping it every certain number of time steps. So let's do this a different way. That's how we would do it in Metropolis Monte Carlo. How would we do it in agent-based Monte Carlo? Any ideas? So remember, agent-based, you just look at each particle it's sitting on. You look at each particle at each time step. So you have some particles sitting on this lattice here. You want to determine if it's going to jump left or right, or maybe sit still.
So we've got 3 events, and we calculate probabilities with Boltzmann.
Exactly. Okay. So what we can actually do is, first of all, take a random number to decide if we're going to try and go left or right. Cool. And then we figure out, well, if I try and go in this direction, what's the probability that it actually happens? That's given by the Boltzmann rate. Cool? And so in this case, it would always happen because we're going to lower it. Right? In this case, we would do so only with some probability less than 1, depending on exactly how big this energy is. Cool? So most of the time we try to jump here, we'd actually save. Cool? Is this all right with people? Yeah? What we're going to do at each time step is look at every particle and evolve it according to these programs. Okay? So we're not going to do this metropolis thing where we just look at one and try and move it and see what happens in the system. We're going to look at each one of the particles and see how they would jump.
So in this, the system is very similar. But I guess if the particles interacted with one another, this would be more different.
Yes, it would. Yeah. Okay, and so how do I actually do that? Well, this is what I tried to explain before. But we need these probabilities, okay? Which is basically, remember, we need these probabilities of particle jumping left or right. We can just construct these from the Boltzmann rate. Okay, with the exception that if we are at the leftmost site, your probability of jumping left is 0. And if you're at the rightmost site, your probability of jumping to the right is 0. Cool? And then what we can just do is, notice we don't select a particle at random anymore. We loop over all particles. And then we select a random number to determine if we're going to jump left or right. And then we do so with the corresponding probability. Cool? And again, we can dump our density. We can calculate our density at each time step and dump that to a file. Cool?
So if the particles did interact with one another, could we still do this? Then it would matter what order we go through the particles, and we'd have to recalculate the probability that we have a particle.
That's a very, very good question. Okay. So when you start having like big time steps that something major happens in, the order of operations starts to matter. If they're interacting. Okay.
What's this method called?
Well, it's not really. It's all Monte Carlo.
Yeah.
I'm just trying to discriminate between. It's not. It's like, as we're going to see, everything we're doing is exactly the same. Okay. But it's just kind of different ways of thinking about it. So in one, you're only concerned with what direction is the system energy going. Right. The other one, you're like, okay, no, I can look at this as a bunch of discrete particles that all have probabilities depending on where they are of something happening. And at each time step, I just look at each particle to see what would happen. That makes sense, right? Cool. And there's a third way we can go about this. What's the third way?
Can we use a Monte Carlo method?
Yeah. And how would we do that?
So you define a rate to jump, and then compare against those rates.
Yeah, and now we're going to make a massive assumption. Okay.
Because we have to choose what the rates are.
Yeah. And how can we get these rates? Oh. We know something about the rates.
So we know the rates are going to follow some distribution. We know
No, the times that they're going to follow this on.
the chance of going in place.
What do you think about the rate of jumping from here to here, as opposed to jumping from here to here?
Because before we would say if it jumps right, it just always goes right. If it goes left, only with some probability. But the rate of jumping right compared to the left.
There'd be a larger rate.
Yeah, it's a larger rate, but like, can you pick a particular number? Can you be like, oh yeah, 90% of the time it's going to go left, 10% of the time it's going to go left.
So remember we talked about Raynaud's process, escape from trap, Kramer's escape. The time scales as an energy barrier.
So
We're
usually,
going to forget about the prefactor.
That's an exponential.
Yeah, so using essentially the factor to that, we can just use the rate that it would go 1 over our rate of jumping to the left and 1 over our rate of jumping to the right.
Yeah. Okay. So we're going to say, and we're going to make a lot of terrible assumptions right now. We're going to say that the rate going from here to here is just the exponential of the energy difference. Okay. Well, the time to go from here to here is the exponential of the energy difference, right? And if we take 1 over that, we get the rate. But if we take 1 over that, what do we have? Over 50. We have the multiple. Okay. So we made some brutal assumptions. Okay. It is not true that the time to go from here to here is equal to exponential. Okay. It scales as that when the energy barrier is high. There are other important factors such as the attempt frequency. Okay. Even more so, just if this is the final state and this is the middle, maybe there's a huge barrier where this actually happens, right? Sometimes you have kinetic, you have chemical reactions that there's a huge barrier between them, right? We're going to make this assumption so that we can link all 3 methods together. Cool? Are people okay with it?
Or we're still only moving in one direction.
Yes.
So in that, if we had like an activation energy, if we like accounted for the activation energy, then this would get it right.
No. No. It's very complicated escape process. It can depend on like the shape at the top here. Right? Because it takes a certain amount of time to get a kick energy enough to get here. Even when you get here, it doesn't guarantee you're going to end up over. Okay, so there's a whole series of this, transition state theory. That you first look at the probability of getting here, and then the probability of actually ending up where you wanted to go. So no, it still doesn't get here. Okay? It's more complicated than this. That is why kinetic Monte Carlo is often used, because as long as you can just do an experiment and observe the rate, I don't care. Right? Cool? Okay with people? But for now, let's make the assumption that it is just the time is that factor, and 1 over that will be the rate. And that allows us to calculate all the rates between these different states. Okay, but they always are linked to the left or right.
And 1 over the exponential of the energy.
Right, which is e to the negative energy difference, which is the Boltzmann factor. Cool? All right, so again, we can calculate these probabilities like we did before, except now there are rates. Cool. And so now what do we do? Well, notice this is a totally different algorithm in terms of implementation, okay? We calculate the total probability by summing up all of the probabilities. Cool? Yeah? We take a big random number, which is going to be our usual random number multiplied by that total rate. Cool? And then we say we just do a while loop. So while we haven't had an event, remember we have to have an event at each time step. What we do is we say I is going to be, oh yeah, this was a check to make sure I was less than my total number of particles. Okay, because I had to be. But what I'm going to do is say if big random number is less than whatever, the probability of whatever block I'm at, then that is the event that happened. Cool? Just like we wrote down here. Right? So what do I do then? Well, that event happens. Okay? The particle is going to move to that new position. I do the usual things that I do. Cool? Like take away 1 from the density here, move the particle to the left, and then increase the density at my new position. Cool? So if that was when if big random number was less than the probability of jumping to the left, Pn. If that's not true, what's the next step? Well, I take off that Pn, And now I check to see if big rand is less than the probability of jumping to the right. Cool. And if that's true, then I do all my usual stuff there. I take one away from the density where I am. I move forward the position of that particle, and I add one to the density at the new location. Cool. If that is not true, I take off the probability of jumping to the right from my big rand. I add one to whichever particle I'm looking at, and I do the exact same stuff for particle 1. Previously it was particle 0, now it's particle 1. And I keep doing that until I find my slot. And my slot is going to be some particle between 0 and n, and it's going to jump either left or right. Cool. Is this all right with people? So it's a way of doing this. Oh no, I erased it. It's a way of doing what was there before.
Yeah.
Okay? We have that big table of all our probabilities. When we march through, we select some random number on that domain, and we just march through and see where it landed. And then that's the event we have the next. Okay?
Just the equation for the log of it is possible. No, it is possible.
Okay. So,
We were already with that earlier.
so this.
Yeah, it's because in the derivation we read it before.
Oh,
Yeah, that's right. Cool, so we select another random number between 0 and 1, and this is how much I increase this. Cool. So, a couple of interesting things have happened. So again, because of the assumptions we've made, everything's going to work out to be identical. But some of these critically different between these different approaches. Everybody think what it is? Yeah, the time scale. Okay. The trouble with Monte Carlo, it's not clear what our time scale is at all. For our particle-based method, we just keep increasing the clock by 1. And at each time step, we evaluate all particles. Okay? And even if none of them move, that's fine. We just add 1 to the clock. Okay? And we always add the same delta t to the clock. In kinetic Monte Carlo, something always happens. And the time we add is not always delta t. It could be a very long time. Cool? So the idea of time is very different between these approaches.
So for a system with some reactions that occur very infrequently, it's I think Monte Carlo for computation to get to a certain like total simulation.
Yeah, I mean, it depends, because you can relate your probability to some time scale in the agent phase method too, right? You can probably scale up some aspects of your system.
And we get into issues if like you've got some event that happens once in a million years, right? Then that event happens. And for that one time step, your time step is a million years, with everything else is happening every day. Your simulation says that for a million years something else happens.
No, it doesn't, because our time step considers the total rate.
Oh, because there's that law in there.
Well, no, even if we didn't do it that way, but it's the total rate of things happening. So.
Yeah, but so if you had
Then the average time step would be skewed to a gigantic number.
Yeah.
Right?
Yeah.
But I mean, because your rate of that event happening is very, very, very small.
Yeah, right, but because all of this stuff we've done for kinetic Monte Carlo recovers the correct stuff in the mean.
Yes.
Then if you have a rare event and your simulation draws that event a couple times, then you're not accurate there.
That is always true for simulations. Okay, it's one of the things you always have to keep in mind with finite time simulations. If you have these long time rare events, whether you see them or you don't, you dramatically skew the results. But is this algorithmically, is this okay? Okay. So let's try and show the results from all three of these and see what happens. Okay. In order to do that, I have to match up times. So what I'm going to do is for my agent-based one, where I look at every particle at every time step, I'm just going to advance time by 1. Okay? For these guys, my time step is all weird and it keeps changing and stuff, right? So what I'm going to do is output it basically every integer. Okay? So as soon as we pass the next integer, I'm going to write it to a 1. Cool? Because I may not actually know what the system looks like at a time of 5.0 exactly. Right? I may end up with like the first, I may go from 4.98 to 5.07. Okay, but I'm going to say 5.07. Cool. And what about from Metropolis Monte Carlo? Any idea what we can do about the time step?
Well, we can make the same assumption about the state processes being Kramer, like simple Kramer processes, because we've already got probabilities in terms of those exponentials. So then we use the reverse reasoning to bring that back.
So we've already kind of done that. So in Metropolis, we only ever look at one particle at a time, right?
Yeah.
We only flip around one at a time. If I want to map this to the other simulation time steps, any idea what my delta t should be? Think about how we can get agreement with the agent-based simulation. The agent-based simulation, we increase the clock by 1. And I look at every particle in the system and evaluate its probabilities to see this jump. Metropolis kind of Monte Carlo. I only look at one particle.
That's one over it.
1 over n.
So once we've done every particle, we've done one time in
Yeah.
equivalently to the other.
In order to map it. Okay. Again, this is not true. This is just so I'm trying to show you guys 3 ways of looking at it, 3 ways of implementing it, the strengths and weaknesses, but also how we can try and map them to each other. Okay?
Yeah.
With brutal assumptions that are not true. Okay?
That's
But
okay.
they can be true in this room today. Cool? Does that make sense to you? Yeah? Okay, so let's see if this actually works. Well, okay, so I'm going to do, I ran the programs we just looked at. For the agent, I just dumped every time step. For the kinetic, I did as soon as we passed the next integer. And for the Metropolis, I dumped them 1 over n, every 1 over n. Cool. And so let's see what those distributions look like as a function of time. I think I start with linear, so I'm randomly distributed. Okay, and then we should see it evolve to something that basically looks at like the log of the energy differences there, okay? Okay, and those are the 3 different Monte Carlo methods. Oh, I gotta stop doing that.
The blue screen.
Right, it's because it's not weird. Just take my word for it.
Just take my word for it. Everything works perfectly.
Any questions?
That's really cool.
Which one's this, Metropolis?
This is all 3 of them on top
Oh,
of each
yeah,
other.
right.
Okay, and so those are the densities at each one of our sites.
Is it green?
Yeah, the green one's got issues at the left panel.
Or is that just because of the time steps that you dump it at?
Oh, they're default color.
Green is kinetic.
Okay, yeah, so,
Yeah, so maybe they're evolving.
well, they're evolving at different time steps and we're kind of
This is pretty good, guys.
awkwardly mapping
Yeah,
time
This is
steps.
pretty good. Come on, this is pretty good. So there's numerical error, of course.
The
We have
red and
10,000
blue agree to within machine precision, and green does.
So red and blue are the identical thing.
So red and blue are metropolis and.
Yeah. Okay. And again, these are words I'm using here to kind of discriminate them, but as we see, they're the exact same thing.
Yeah.
Okay. It actually gets very confusing. It's going to get even more confusing. Okay? Because we're going to start talking about rules-based simulations, which again deal with numbers. So essentially, those are all Monte Carlo. Okay, but we're going to go some of them. Metropolis basically means your metropolis Singapore. Okay? If you're kinetic, great. Your metropolis doesn't give you time. If you're kinetic, give you time. Cool? And then what we're going to keep looking at in the course is not so much metropolis, not so much kinetic, but instead what I'm calling here an agent-based Monte Carlo, where every time step we look at all the particles and stuff happens. And I want to expand this because we want to start bringing in different rules. Just arbitrary. This happens in this. Okay, just to see what we can get. Cool? But I want to make a connection here, as nebulous as it is, as incorrect as it is, that all of this is kind of the same stuff. Okay? Yeah.
From my experience in co-op, this stuff that we're learning right now is actually really subtle, and a lot of people, a lot of professionals don't properly understand it. For instance,
It took me a while.
Yeah.
That's why I haven't marked any of your assignments yet. I finished this lecture in a faculty meeting.
Oh, that's awesome.
Yeah, not really.
well, so
I'm not sure the dean thinks it's awesome.
they do this kind of thing in reactors. They want the Carlo to do neutron simulations of the core. And what they care about a lot of the time is the criticality of the core, whether it's a self-sustaining chain reaction or not. And so they use approximations, and they use essentially like metropolis or whatever, like time unrelated approximations to get the criticality parameter. And a lot of professionals think that that gives you the behavior in time.
The big rate. Yeah.
But ultimately, they've set it up as an eigenvalue problem independent of time, and they use this evolution that's iterative, so it looks like your system is evolving.
Yes.
But that's not meaningful in time, and like that's something that nuclear engineers running reactors still don't fully grasp. And there are time-like methods, but in practice, they'll be used.
Right.
So anyway, just understanding this subtlety makes you kind of a boss.
So it's tricky. Because at the same time, there is some connection to how it evolves in time. Metropolis will give you some indication of it, but it doesn't necessarily give you, okay, this is the time now. Okay, that's more subtle. We have to bring in these attempt frequencies, all this kind of stuff to actually get what the actual rate is. And then you have to get into this whole rate theory, which is its own field, which is a good project.
But in practice, a lot of the time, you don't care about the intermediate. It's like if you're
no. So Metropolis, if you're just trying to figure out what the long time limit looks like, go ahead. God bless you. Okay? And so that's what a lot of people use it for. And its original use was for that as well.
But this is definitely one of those things that a crusty old man at some conference will like pick on you on if you try to say that you're getting the time evolution right.
Well, they're not necessarily crusty, they're not necessarily old. And they're at a conference, they're EOIT, and they will do the same thing. Okay?
So there was
because it's something when people, there is half the people that do simulations out there, well, maybe not half, but a significant portion of the people that do simulations out there, when they hear Metropolis Monte Carlo, they're just waiting for you to say time. Okay?
Yeah.
Yep.
I have a question with the jump size.
Actually, when you just say Monte Carlo, they're waiting for you to say time. And that's why you need to know if it's kinetic. Cool. We're all cool. Okay.
I was curious about the jump size and what we're drawing over there. So, like, in comparison to how thick or wide these steps are, to the jump size that we're taking. Jump size.
But I haven't really. I use particles to motivate this, right? But in a way, I haven't really specified. So this doesn't have to be a spatial dimension. It can be just a system that has 5 states that are linked in this order. So the system can go from this state to this state, and there's an energy difference. And by having the particles jump around, what you're actually doing is an ensemble average over a whole bunch of independent systems running at the same time and seeing how often you find the system in each one of them. So it actually doesn't have to be a particle at all. It can be something totally abstract. Not that the system's totally abstract. We go even more than abstract, I think. Okay. And again, you can take all three of these approaches, but beware that when it comes to time, things get tricky. Okay, and that's why when we did do Monte Carlo simulations of particles jumping around, it didn't look like this. It really did it. We had to pay a lot of attention to what the time step was. Cool. Remember, we had it on a lattice, and we had this time step that was dependent on extra force. Blah, 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 blah. Cool.
But yeah, like the really cool thing about this kind of stuff is that you can go into a lab and measure individual rates of reaction in like simple experiments, and then you know, without any of the theory behind Kramer's case and whatever.
Yes, totally.
You know your exact rates of reaction. You get that
Absolutely. Yes. Let's see, this guy, I think. So these are my different distributions. And why am I bothering to show this? I forget. There's a reason.
It's like the evolution, or just like
It's the evolution.
Is the solid blue line volcanic?
No, that is the long time solution. So I didn't actually put the Boltzmann on here.
So what's red and blue?
Different times.
Oh, I see. Yeah.
Cool.
Oh,
Is that cool?
Different time of blue.
Slightly different time, I believe.
So these are.
But
Yeah.
yeah, at very short times they're different, as you may expect. Cool. So this is kind of delving into Monte Carlo simulations a little bit, looking a little deeper at what they are and stuff like that. Cool. Now I want to come back from Monte Carlo. I don't want to do Metropolis or kinetic Monte Carlo. I want to get back to our nice agent particle-based stuff. So we just think about particles doing stuff according to some interactions. Okay? Martin.
I haven't thought about what we just finished before leaving it. A few people on the assignment that we did yesterday had their posts shifted, which led to these metastable states lasted forever.
Yeah.
Right? Which brings up the point that in these systems, the methods that find the long time state kind of presume that there is a long time state that's going to be achieved within some reasonable amount of time.
Absolutely.
So if you're going to get stuck in some medium state forever, then Metropolis might give you a very misleading.
Yes, and there's whole ways of dealing with this too. Does anybody know? It's a huge problem in physics. How do you find the global minimum of a state? Particularly when you have like a multi-dimensional potential landscape. Stuff gets crazy fast. Can anyone think of an example?
If you're trying to find the global minimum, then you can turn up the temperature so that everything's accesses all the states, and then turn it down after.
What's that called?
Annealing.
Yeah. Okay, so you can do simulated annealing. All right. You take your system, you bring down the temperature, right? It starts to go to some minimum. That's a local minimum. Could be a global minimum. We don't know. Turn the temperature up, bring it back down again, see what happens. Okay. This is called simulated annealing, and it's used a lot.
So you're basically just like blowing your simulation up and then waiting for everything to fall down.
You're not blowing it up.
And then going, oh, that's the lowest bit.
No, but remember, we're dealing with potential landscapes, right?
Yeah.
So you have some potential landscape, but this is just in one dimension. And now
Yeah,
start
you
thinking
have,
about
like, three-dimensional.
now start thinking about something like a protein.
Yeah.
Think about how many dimensions that has, right? It's crazy now, right? So how are you going to go through that? Well, you want to figure out this state here, except now on an n-dimensional plane, right? Or I guess not plane, n-dimensional surface. Okay. And what you're going to do is you bring up, so if you're here, you want to bring up the temperature so that you can get over here.
Yeah.
Cool. So that's it. You're not blowing anything up.
Well, like I can imagine like just, like, throwing stuff in the air and then just waiting for it to all fall back down again. Like, oh yeah, that's my lowest state.
Kind of.
Yeah.
But
I mean, proteins are a very good example of this.
Yeah.
Protein folding is a crazy process where you find the global minimum in a like, ridiculously complex dimensional.
Like in the team folding.
And it's been a huge question for years and years. How do proteins do this? How do they find a way that another interesting point.
My question was on the connect. Could you have non-equal connect, like Carlo? I guess so. You just incorporate the external force in the rates, or would you incorporate external force? If they get an external force.
Yeah, no, it has to be in the rates.
Okay.
Yeah. Everything's in the rates. Cool. Any other questions on this?
Yeah, I was just gonna say that sometimes simulated annealing is used for finding the global minimum, but sometimes you don't want the global minimum. You're trying to reduce like how a specific system evolves under certain conditions. Okay, in which case, just finding the global minimum is actually wrong. Because Metropolis will try to find the global minimum, basically, but that's not actually what you want.
Right. Cool. Good. Okay. Coming back to that, let's get back to particles. Okay. And what we want to talk about now, before we can do some more interesting stuff, is basically let's spend some time talking about how particles can interact. Okay. Both non-bonded interactions, so we can have attraction between particles or repulsion between particles, and also bonded interactions. If two particles are bonded together, or if we want to build more complicated objects out of particles, how can we do that? Cool. In order to do that, there's a topic we have to talk about. Everyone in this room probably knows it, but I got to wedge it in somewhere. What are periodic boundary conditions?
I don't know how you implement them. I don't know if you back definition. Just
It's like in the Matrix when he's stuck in that subway station, he runs up to one side and he comes to the other.
It's what?
Like in the Matrix when Neo is stuck in the subway station.
Periodic boundary conditions.
Yeah. I think we all know how to implement them. I don't know if we know an exact perfect definition of them. We just kind of
Exact and perfect is a really high standard. Way too high for this case.
all right. We just basically have a system mirrored on all sides.
Not mirrored.
Or I guess not mirrored, but like repeated.
Yeah, I heard you.
Why do we do this? Well, lots of things are easy.
I figured as far
Well, like,
as
there's a lot of mathematical advantages. Like a lot of methods work on.
Math advantages?
Computation.
Well, like Fourier transform methods work on periodic boundary conditions. Won't work on other boundaries.
Okay.
so
Periodic boundary conditions.
So there might be math applications. Are there any immediate physical applications?
so within a given cell, we always know how many particles will be in there. So if we said the cell has a density of 3, if one dot moves way off to the right, it'll just pop in on the other side, so it still maintains that density.
That seems like a hammer.
Okay.
That's all we need.
If you're
We could just put walls here.
Right.
if you're modeling a big
Why do we not want to put walls there? Why do we want to actually? So to be clear, what we're doing is we're taking the same system, replicating it over here. Okay. All right.
See how
But-
it's in your,
Yeah. What do we gain?
you have a nice solid.
Awesome. Exactly. We go from a finite system to an infinite system. Cool. Finite systems. What's the problem with finite systems?
Boundary.
Yes, they're finite, which means they have boundaries. Boundaries have huge effects on your results.
But you guys will put boundaries.
Okay. Yeah, we touched that. So this is a way to try to ameliorate this. Be careful. PVC is not a magic bullet that gets you away from finite size effects. But it is a great first step. Okay. So what do I mean by that? Well, this particle here, if I don't have boundary conditions, it doesn't see anything over here. Cool. Now it can see this stuff. Cool. So I go from having a vacuum to having stuff. It gets even more important when you start to think if this is actually filled with fluid, right? I don't have anything on my boundaries, the fluid is just inescapably happening. If I put in walls, I'm going to have all this structuring of fluid in that wall. Okay, my system's big enough. I can do this, and I'll have pretty much decent behavior fluid at all places. Cool. We have to be careful. This guy can see this guy here. Can you still see him here? Here, yeah.
Depends on how long your interactions are, but yes.
Right. So this is why our maximum interaction cannot be more than half a box. Otherwise, you start to get weird artifacts and you're seeing the same thing. Okay.
Another half the box.
Your maximum interaction cannot be greater than half the box.
Oh. I think if you had a domain that was one part big.
Yeah.
Or I guess, yeah.
So we're kind of making a pseudo box around a single particle where it can only see things inside that kind of negative element box.
Yes, exactly. Yeah. But that's the maximum limit it can see because it doesn't have to see things that far.
Yeah.
Okay. Because otherwise you start seeing the same particle twice, and that's obviously going to be crazy. Because all of a sudden, whatever influence this guy has on this guy could be totally different, and it's going to be totally symmetrical. Cool. All right. So be careful when you use PDCs. We need a big enough system. Okay. So interestingly, you mentioned the matrix. Where else do you see periodic boundary conditions? Pardon me? Pac-Man, absolutely. Video games like crazy, right? So many video games. You leave here, you come back in here. Okay? You leave here, you come back in here. Incidentally, if this is true, what kind of world do you exist in? Yeah,
huh?
Right? Because you're wrapping this end around like this. And you're wrapping this end around like this. The only way those can both be true.
Awesome. You look at a spaceship and you go straight in space. When you eventually reach the same point you're at, you're in it.
We don't know.
Right, you start here, you got straight, and you can reference,
Yeah.
you go around.
That's just you doing the big Pac-Man.
Yeah. Cool. So a lot of video games take place.
Actually, and also some video games have periodic boundary conditions on the left and right and not top and bottom, which have mixed boundary conditions, which are hard.
Yes, yeah, that's true too. Cool. Okay, the next stuff we're going to talk about is a whole bunch of different interactions, so non-bonded interactions. Okay, you just have particles interacting. We've already seen some of this. We're going to go through it in more detail. We've seen excluded one. Okay, and we'll talk about that in a little bit more detail. Then we're going to start joining things together. If I join two things together, I can have bond, right? If I join three of them together, I can now start defining constraints on angle. Cool. And if I have four of them together, I can now start putting constraints on planes. So I can keep something in this configuration as opposed to it rotating like this. Cool, because I can still satisfy both of these bond angles, but it would be a different configuration. We're going to see, oh, I missed one. No, let's get the bond angle. Okay. We're also going to see how the bond angle can give us stiffness. Okay. And we're going to see that if we start combining all these potentials together, we can start building complicated objects. Like, let's say, red blood cells. That's just an example. Okay? And then this will give us the tools to start building complicated objects and doing simulations. Cool. So we'll do that tomorrow.
Yeah.